Okay, so last class we left off talking about how we do hypothesis testing. So we had the steps for not only when we were looking for where the population mean is and we only had a sample mean, but when we wanted to know where the population proportion is and we only had a sample proportion. So the steps are very similar. We walked through two approaches. One was called the p-value approach, the other was the critical value approach. So I'll try to do both of those. For every problem I show you today, I'll show you both approaches and show you how we get to the same answer no matter which approach we use. Right? So the one that we didn't cover yesterday, I had to let the dog out of the room. So the one that we didn't cover yesterday was if we want to know where the population mean is, but we don't know what that population variance or standard deviation is, or we have an unknown population variance or population standard deviation. So if that's the case, the steps will look very similar. We still have to figure out what the null and alternative hypothesis are. We still have to know what level of alpha we want to test against, or test that. And then steps 3 and 4 are kind of interchangeable. So we can find the critical value, right, using the type of test, what alpha is, and now we'll have this additional component called the degrees of freedom. So if we go back to last week, and we looked at confidence intervals, and we had to look up that t-value for confidence intervals, it's going to be very similar here. Now our critical values are no longer z-values, they're now t-values, right? They're coming from a student t distribution. So once we find those critical values, we'll calculate our test statistic. Now this will look very similar to what we did when we had a known population variance and we were dealing with kind of population means. It's just now we use the sample variance instead of the population variance. And so we no longer have a z statistic, we have a test statistic. And then of course the last step, using that critical value in our test statistic, figure out if that test statistic or that t statistic falls in the rejection region. So, there we go. So let's say I've got a couple things here. Oh, let me close this blind. That'll probably help. So, first of all, I always kind of explain it this way, right? So, last class we were calculating z statistics. Now we're doing t-stats. These are both types of test statistics, and really, the first letter is just identifying what type of distribution are they coming from, right? If it's a z-stat, it's coming from a standard normal distribution. If it's a t-stat, it's coming from a student t distribution. Okay? Now, the three types of test statistics we could have was when we had only a sample mean, right? We had the assumed true mean, and then divide by the square root of the variance over the sample size, where this denominator represented the standard deviation of our sample means. The next one we had is if we were dealing with sample proportions, we took the sample proportion minus the assumed true proportion divided by the square root of the assumed true proportion times 1 minus the assumed true proportion over our sample size, where the denominator here represented the standard deviation of our sample proportions. Right? So now we're going to have not a z-stat, but a t-stat for our sample means. So we'll take that sample mean value, subtract the assumed true mean, so same thing as before. But now we'll divide by the square root of our sample variance over our sample size. So now this denominator still represents the standard deviation of our sample means. It's just that we're using that sample variance, and here this should be an S, sorry, it's a little bit unclear, instead of that population variance. Right? So three different types of test statistics. When we have a sample mean and we have a known population variance, we're dealing with sample proportions. Those two situations, we're using that standard normal or z table. And then the one situation where we use the student t is when we have a sample mean, but we only have a sample variance. Okay? All right. So we've got our steps. Hopefully we've kind of related it to what we've done already. So now we'll work through a few problems. Right? So the first one we have is, let's say we've got this, I want to test the hypothesis that the average home value in Muncie is different than 90,000. Right? So what we want to test for is going to be the alternative hypothesis. So when I say what I want to test for is it different than 90,000? What I'm really saying is it any other value than 90,000? Or mathematically, we're saying is that not equal to that 90,000? So our alternative hypothesis is going to be, is that population mean not equal to or anything different than 90,000? So what's the null? Well, we assume the exact opposite is true, so we assume it is equal to 90,000, right? So we've identified the null alternative here. We've got a sample of 51, so that's our sample size. We've got an average, sample average we found from these 51 homes, or a sample mean of 85,000. And we had a sample variance of, what, 100 million here? So we've got our null alternative hypothesis. So what type of tailed test would this be? Well, we have a not equal to sign in the alternative hypothesis. That's probably one of the easiest ones. We know that we've got a two-tailed test. Okay? So we've got a two-tailed test. So we want to identify the critical values. Well, we know these are going to come from a student t distribution, right? Because we only had a sample variance, right? We also know that if we have two tails, alpha gets divided amongst both of those tails, right? So I'll kind of give you a setup and a drawing for what it would look like if we only did one of these alpha values, right? So I've got three here, the 1, 5, and 10% level. Let's just do for alpha equal to 0.1, right? So if alpha is equal to 0.1, here, 0.1, if we can see that, then what we're thinking about is I'm dealing with a student t distribution, and I want to find the critical value, but for a two-tailed test, I should know I'll have critical values, right? One positive, one negative, because half of alpha is on each side. It's very similar to what we're doing with those confidence intervals, right? Alpha gets split up amongst two sides, so what value would give me half of alpha? Well, half of alpha here is 0.1 over 2, or 0.05 on both sides. So I'm going to look up, I know the area I want is 0.05, and the only thing I have to figure out with my student t distribution is what are my degrees of freedom. So I know that I want 0.05 in that tail, and I can find my degrees of freedom by simply taking the sample size and subtracting 1. So let's go to our t-table. The area I wanted in the tail we said was alpha over 2 for a two-tailed test, so 0.05 is what we kind of decided on. My degrees of freedom, well, my sample size was 50, right? So my degrees of freedom would be 50, sorry, my sample size was 51. So my degrees of freedom would be 51 minus 1, or 50. So you go down here, 0.05, degrees of freedom 50. 1.676 would be my critical value. Now I'll have a pair of critical values there because, right, 1.676 rounds to 1.68 here. So I'll have a pair of critical values because there's one on the right side, one on the left side, or there's one of them's positive, one of them's negative. So for a two-tailed test, we should always have pairs of critical values. Right? I could then do the same thing, look up an alpha of 0.05. Well, it gets divided by 2, so 0.025. Same degrees of freedom. So if we go up here, 0.025, at degrees of freedom 50, 2.009, and then an alpha of 0.01 getting divided by 2, 0.005, at degrees of freedom of 50, 2.678. So if I round those to the second decimal, that's how I get these three values here. Okay. So those are my three critical values, and kind of have a a reminder on this slide of how we find those, but I kind of walked through the actual table here just now so that we can see that. Okay. So the next step is I know my critical values. Well, I'll show you in a second. I would plot those critical values, and then I'll plot my test statistic against those. But before I go to plot them, let's just figure out what my test statistic is. Okay. So I've got this set up, right? How can I figure out what this test statistic is? Well, I had that equation for the test statistic that looked very similar to what we were using before. It's just that the population variance got replaced by the sample variance. Okay? So if I look at this, one thing I can notice is the assumed true mean of 90,000, I found a sample mean of 85. So I found something below that assumed true mean. So remember, the test statistic, no matter if it's a z statistic or t statistic, the interpretation still is the number of standard deviations away from the mean. It's just now it's the number of standard deviations away from the assumed true mean. Well, if the assumed true mean is 90,000 and I found a sample mean of 85,000, that's going to be below, right? So there's going to be a negative value, right? It's going to be a certain number of standard deviations below. So are we ever going to need to show how we find the critical value? No. So I had a question come in. So you don't have to kind of justify how you found the critical value. You will have to know the process that you can look them up, or like someone asked, you can memorize them. Now the problem with memorizing them is if it's from the student t distribution, right? I mean, you can't memorize all these, right? It's very easy to memorize what those critical values will be when you have a standard normal distribution, like the ones that we covered, the two types of examples we covered yesterday, which is when I know the population variance or I'm dealing with proportion. But when you don't know the population variance, all you have is a sample variance. It's going to be very hard to memorize these, right? They change depending on the degrees of freedom. So you're not going to have to show how you found the critical value, but you will have to know how to find it using this table, if that makes sense. Okay? Hopefully that clarified. So if not, feel free to kind of ask a follow-up question. But as I was saying, we found something that was a certain number of standard deviations below the assumed true mean. So it should be that this test statistic is negative. So B or D is probably going to be the answer. From there, I mean, I'm guessing it's not 0.002 because that would have to be that we found something very, very close. We're about 5,000 away. My guess is it's not going to be that low of a test statistic. Sure enough, if we plug everything into that equation, and you'll have this on your formula sheet. So if you look in that practice materials, you should have the formula sheet. You'll see these test statistic equations. Once I have identified that I have a sample mean and only a sample variance, calculating the test statistics should be pretty easy. Right? The test statistics should be easy to calculate here. Once you've identified the correct formula, it's just a matter of plugging those values in. Right? I found a sample mean of 85,000. The assumed true mean was 90. Sample variance, sample size, is about negative 3.57. Okay? So I had kind of drew this ahead of time, so let's see if I can find where it was at. There we go. So let's say, let me zoom in a little bit here. We have this problem where I found this sample mean of 85,000. The assumed true mean was 90. If I then think about, okay, where are my critical values going to be? Well, I looked them up. I found they were positive and negative. Oh, I have these labeled backwards. Well, I guess we're just going to have to draw this one on the board. That's okay. I was trying to get that together quickly this morning, and I was just writing numbers down and realizing I wrote them backwards. So, for this problem, what we're doing is, so if I get this to autofocus, there we go. Maybe. So, I've got student t distribution. Come on, focus better for me. Maybe. Switch off and on real quick. Let's see if this gets better. All right, there we go. Okay, so I looked up my critical values. I had positive and negative 1.68 was the first one. So here's my rejection region. I had positive and negative 2.01. Here's my rejection region. And then I had negative 2 positive and negative 2 I think it was 68, if that's not right. Let me see, what was that? Yeah, it was 68. So here's my critical values, right, and my rejection regions. I found negative 3.57 as a test statistic, which is going to be way out here, so I plot that. It's clearly in the rejection region for every single one of these different alpha values. So for alpha is equal to 0.01, 0.05, and 0.1, right? That test statistic of negative 3.57, it's a little bit clear, right? And I'll kind of write this again. clearly that's in the rejection region for each one of these different values. Right? Now, I think the easiest way to do these problems is to draw those critical values first. So plot where those critical values are. Once you have those critical values plotted, the next step is draw where that test statistic would go, right? And if it's in those rejection regions, which the rejection region, once you draw the critical value in there or plot the critical value, it's just the area that's more extreme, right? So if the critical value is positive, it's going to be the area to the right. If the critical value is negative, it's going to be the area to the left, okay? All right, so we'll go through another example. So let's say we've got a second example, and we're back dealing with this birth weight data. All right, so we know that what the mean birth weight is. Oh, so the assumed true, we're testing for, testing against. Looks like we're testing for whether or not the average birth weight is less than 3,287 grams. Okay, so is it less than 3,287? So the assumed true value should be, is it less than, greater than, or not equal to 3,287? But what sign do we need? Well, what we want to test for is in the alternative hypothesis, and here what we want to test for is whether or not it's less than. So we'll see a less than sign in the alternative hypothesis, and we want to test for whether or not it's less than that 3,287. As I mentioned yesterday, the sample mean you find should not be in the null or alternative hypothesis. That's not, you're not putting that sample mean as that value. It's some value that maybe you see reported or that someone tells you that you want to test against or test for whether or not it's less than or greater than or not equal to that value. So here we want to test for whether or not it's less than, so we're going to be looking at that as our alternative. We'll assume the opposite is true for the null, which is that it's greater than or equal to that value. Okay? So what type of tailed test do we have here? Well, the type of test, we go to the alternative hypothesis, we see a less than sign. So is it less than with a left-tailed test? Right? So one thing we should know about a left-tailed test automatically is that our critical values, right, should be negative, right? If we're dealing with the left side of the distribution, I close the blind here, so maybe this will help a little bit with the autofocus. If we're dealing with the left side of the distribution, right, we know the mean of the student t distribution is 0, so our critical values for a left-tailed test should be negative. For a right-tailed test, they'd be positive. And if it's a two-tailed test, we have one of each. Right? So we've got a left-tailed test. We can look up our critical values, but at least starting out, we know that they're going to be negative. Right? So which of these are even possible options? Well, if I gave you this on an exam, hopefully once you've identified that it's a left-tailed test, you look at this and you say, there's only one set of critical values here that even makes sense. Because for a left-tailed test, they should be negative critical values. But how would I find those? Well, as someone mentioned earlier, you could memorize them. Although if it's a student t distribution, you'd have to memorize a bunch of different degrees of freedom. So here, our degrees of freedom would be what? N minus 1. So 400 minus 1 is 399. We talked about with the confidence intervals that if you ever get a sample size that's like over 100, you basically can use the standard normal distribution to approximate what your critical values would be, or what your z or t values would be. So anything over 100, notice, these are basically the same values out to the, especially the second decimal, but even out to the third decimal once you get high enough. So I'm not going to try to trick you on the exam. I'm either going to give you something where the degrees of freedom is well over 1,000, or it's going to be under 100, right? And so, and if it's under 100, I'm not going to put it in between these. I'll give you it so the number's in the table, right? But we could use the standard normal distribution to approximate here. If we do that, that's this last row. We said instead of using the standard normal table, really to find these critical values, we could just use the last row of the student t distribution, because if we ever had degrees of freedom of infinity, the student t distribution that we'd be using would be exactly equal to the standard normal. So we use the approximation of the standard normal values for alphas of 0.1, 0.05, and 0.01. So we'll use those three columns. So 1.28, 1.65, 2.33. Right? Now, if I look these up in this table, what I have to remember is, oh, those are the values I want, but I'm dealing with a left-tailed test, right? I've got a less than sign in my alternative hypothesis, so it's those values, but they should be negative, okay? So I've got my critical values. The next step is, okay, what is my, so I can look these up. Next step is, what's my test statistic? Well, once again, it's just a matter of plugging those values we have from our, the values that we're given into that formula we know gives us the test statistic. So first of all, I have this assumed true value of 3,287. I found the sample mean of 3,132. I found something below the standard, or sorry, below the assumed true mean. So I'm going to be a certain number of standard deviations below. So once again, I know my test statistic should be negative. I think I got lazy here and kind of duplicated this. This is supposed to probably be a positive 0.123. But really, the idea here is I found something that's quite a bit, far away from that assumed true value. So it's probably going to be a test statistic that's a little bit greater than 0.1. Right? But I don't know for sure, so I can plug those values in. I plug in the sample mean I found. I plug in that assumed true mean, sample variance, sample size. Sure enough, I get about negative 4.67 as my test statistic. Now, one thing we should be thinking about, let's plot this, and then I want to kind of review something. So, nope, that's not what I wanted. I want the pictures. Here's pictures. So here, I've got 3,287 was an assumed true mean. I then plotted my critical values, negative 2.3, negative 1.65, negative 1.28. Those corresponded to, this shouldn't be 0.01, sorry, this is 0.1 right here. I was trying to write these quick before I got on. So here's my three different critical values. Here's the rejection region, right, the area to the left for a left-tailed test. I then turn this 3,132, which was my sample mean, into a test statistic. It's 4.67 standard deviations away from that assumed true mean. So it's very unlikely this is the true mean, right? If this was the true mean, then the sample mean I found to be 4.6 standard deviations away from that, the probability that I saw something that many standard deviations away from that assumed true mean, if it in fact was the true mean, is essentially zero. Right? If I try to look this up in the table, so I go to my student T table, and I say, okay, at the degrees of freedom of even 500, it's a little bit higher than 400, but if I try to look up 4.67, well, 2.5, the area to the right of that, or negative 2.5, the area to the left of that would be 0.005. So 4.67, then the area to the right of that would be approximately zero, right? Anytime we're more than like 3 or 4 standard deviations away from the mean, right, or we have a test statistic that's 3 or 4, or negative 3 or 4 or larger, well, the area to the left of this is going to be pretty much zero, right? The area to the left of negative 2.3 was 0.01. So the area to the left of negative 4.6, I mean, that's going to be approximately zero. So when it gets plotted, it's clearly in all the rejection regions. So we reject at the 90, 95, and 90% level. Once again, this alpha should be 0.1. I apologize for that. But if we wanted to come up with a p-value approach here, well, the p-value is the probability we saw something, this test statistic, this many standard deviations away from the assumed true mean, or something even further away. And so that probability, that area to the left, would be approximately zero. If the p-value is approximately zero, well, that's going to be less than any alpha that we can look at. And so we would reject at every level if we use the p-value approach as well. Now, one thing that I won't do on this exam is when we have to find the p-value for a student t-distribution. So where is it? There we go. Let's say the degrees of freedom was 50. If I gave you a test statistic and said, what is the p-value? And let's say it's a right-tailed test. And so it's we're looking for the area to the right, which is what this table kind of shows us. So we use that degrees of freedom of 50. And I said, well, let's make it easier. Let's say we do the degrees of freedom of 40 so I can show you the column headings. And then I told you, okay, the test statistic is 2.3. So you try to find 2.3 here, but you can't. You're in between these two values. So if you found something in between these, you know the p-value would have to be in between 0.025 and 0.01. I'm not going to make you look those up for this exam. Like if you ever have to find a p-value, it won't be a range. If I ever ask you to find a p-value using the student t-distribution for this exam, I would have to say something like, all right, the degrees of freedom is 40. Your test statistic was 2.42. What's your p-value? Well, 2.423 is exactly one of these numbers, so the area to the right of that would be 0.01. That's your p-value. Right, I would give you one of the numbers in this table. I won't ever kind of give you one that's not and make you put the p-value within a range. But you would have to do that in practice, right? Or you could use Excel, which right after I get done with this lecture, I'm going to do, I'll have it kind of live streaming as well, but I'm going to record the tutorial or kind of template example for Excel today as well. So we'll see how we can do that. All right, so it's a little bit harder to look up p-values using the student t-distribution table because we can only display 6 of the possible test statistics for any 1 degrees of freedom. So I would have to give you exactly one of the values that are in this table if I asked you that on the exam. But on Excel, I could ask you any test statistic at any degrees of freedom and you can tell me the p-value. Okay? All right, so I think that's actually it, but I do want to go through one more thing. I'll draw something here. Yes, because now I just have a recap. Right in the slides, I have a recap of the steps for the p-value approach, the steps for the critical value approach. They're both very similar, both lead to the same kind of decision. I then have 3 slides, which I'll then walk through in the Excel example here in just a second. But I do want to go and draw one more thing for you. All right, so when I'm talking about whether or not we reject this null, or we're finding evidence that goes against the null enough, let's think about it this way. I want to kind of give a better maybe kind of a visual of this. Let's see if we can get the lighting to be good on this board. There we go. Okay, so let's say we're doing the one that we had today. We're doing with sample means. Let's say we assume, I don't know, the mean is 50. I don't know what the example is. We'll just use a couple numbers for it to make sense. Let's say I see, I don't know, 40 way over here. All right. Well, let's say I turn these into t-values. All right, turn this into a test statistic. I see it's like -3. Right. So the area to the left of that, this is approximately 0. Right? So the p-value is very, very small. It's less than any alpha. I can reject that this is the true mean with any level of confidence. I could reject that it's a true mean with 90, 95, 90, 99% confidence. Right? It's more likely, let's see if I got another color over here. It's more likely that if I saw 40 as the sample mean, well, it's so unlikely that 50 would be the mean if I saw 40. It's more likely, let me see if I can draw this. I don't want to draw it too extreme here. Let's say, there we go. It's more likely that the distribution of our sample means is actually following something like this, and that the actual mean is going to be something a little bit lower. Now when I turn 40 into a test statistic, it probably won't be -3. It might be something more like -1.5. Right? So that's kind of the idea. The reason why we were rejecting this is because the probability is so small, if that's how many standard deviations away I am from that assumed true mean, that it's likely that the true mean is something closer to what I saw. So that's kind of the general idea of what we're doing with hypothesis testing. Hopefully that clears it up a little bit, or kind of makes, just kind of talking about it in a different manner. I would also kind of suggest going back. Yesterday we had this photo that I kind of pulled up, and if you want to pause the recording on it, or today we have it as well. But I think this is a pretty nice little visual, and I kind of give you both examples, one where it's a right-tailed test, one where it's a left-tailed test. For the right-tailed test, I'm showing you why, if the test statistic is greater in absolute value than your critical value, well, the area to the right of the test statistic is the p-value. The area to the right of the critical value here is alpha. So if the p-value is less than alpha, the test statistic has to be greater than the critical value. And so in both cases, we would reject, right? When the p-value is less than alpha, or the critical value is less than our test statistic. Now, here I gave you an example for the left-tailed test. Similar idea, it's just now I'm showing you where this is a situation where we would fail to reject, right? Because the p-value here is greater than alpha, right? We only reject if the p-value is less than alpha, so we fail to reject here. And we fail to reject because if we think about the rejection region, the critical value here, for a left-tailed test, the rejection region is to the left. My test statistic's not in that rejection region, and it never will be as long as that p-value, right, that area to the left, as long as that's greater than alpha, I will never have a test statistic that falls in that rejection region. So this is a real nice kind of depiction I would go back to. Pause in both the slides. I'll even kind of put this up in a file on Canvas so that you could, if you wanted to, print this out or kind of pull this open. Okay. So that should do it for today's kind of finishing the lectures for this week. Like I said, I am going to now talk a little bit more about hypothesis testing, but do it in the setting of Excel. So I'm going to stop the recording here, make this a video, and then start a new separate video that is walking through Excel. So hopefully things are kind of, I know things are moving quick, especially since they're online, but hopefully these recorded lectures are helping. I think the recorded Excel templates will really help now that I can kind of have a board. And if you ever have any questions, I know that, like I said, my webcam's isn't the most expensive, and it's autofocuses. So if you ever have any question in the recording of, well, what was that written there? I couldn't quite make that out. Remember, you can pause them, but also ask me, and I'll make sure I let you know. Or if on some of these photos that I've now started creating ahead of time, you can't quite make out what something is, please reach out, ask me, and I'll let you know. Also, any feedback on what's most helpful from these recorded lectures, or anything that I'm doing, or anything that maybe you think I could do or add in that would be helpful, please let me know. I'm kind of having fun kind of learning how to do all this, so any suggestions or advice is welcomed. Okay. All right, we'll end the recording here. We will have the exam next week as well, so all the practice materials are up there. I'm going to try to record something Friday. That's me kind of working through a majority of that practice exam A, so you'll have that when you're studying as well. And then next week, I'll release the exam on Tuesday. Whenever I release it, there will be a 48-hour period, or maybe a little bit longer, for which you can get on Canvas and do that. I have to get the whole exam kind of written into Canvas. Well, there's ESPN app going off in the background. But once I get that released, there'll be about at least at the very minimum a 48-hour period where you can get on. There'll be like a slight time limit on the exam, probably a pretty long one, something like 90 minutes or 2 hours. That way timing's not an issue. And you just have to complete the exam at some point during that allotted time slot. Okay? All right. It's going to end this for week 10.